మెదడు
Steven, sir?
Yes, sir.
Yes, sir. Can you switch on your yes. Okay, right, sir. Okay.
వీళ్ళైతే అయిపోద్ది FDP. FDP వీళ్ళైతే అయిపోద్ది. సర్టిఫికెట్ అంతే. సరే.
Participants, please mute your mic.
ఏదండి?
Dear participants, please turn off your mic. Good morning, all. Welcome to the FDP AI Innovations on Healthcare and Medical Technology. First of all, I would like to invite today's keynote speaker, Dr. Steven Fernandez. Thank you very much, sir, for accepting our invitation. In spite of your busy schedule, you are come forward to take this session. And I would like to give a brief introduction about today's keynote speaker, today's session speaker, that is Steven Fernandez, sir. This is only brief sorry for the disturbance. Because some technical issues, just my Star had published articles in highly selective artificial intelligence values. His current research area is focused on using artificial intelligence techniques to extract useful patterns from big data. This includes robust computer vision and natural language processing applications using deep learning and computer-aided diagnosis using medical image processing. Thank you very much, sir, for accepting our invitation. And I congratulate as well as I hope our participants will enjoy this session. We'll have a great learning day. Thank you very much.
Thank you, sir. Good morning. Could you please enable the screen sharing, sir?
Yes, sir. 1 minute. Yes, sir. Now you can share the screen,
Thank you.
sir.
Okay. Okay. Good morning, everyone. Welcome to this session on AI and health disparities. I thank AICT Atal FDP program on AI innovations in healthcare and health technology for giving me this opportunity to share some insights on the research that is going on AI and health disparities. So I'll start from the basics. So today's presentation flow would be starting from very basic idea of AI and what exactly is health disparity and how data analysis and predictive modeling is built for health disparity. And we'll look into one use case of deep learning based classification in this health disparity sector. So, to start from the basic, we all know AI is a field of computer science which develops systems, or these systems are built to assist human beings or to assist human capabilities. Here, the end goal of AI is not to replace humans, but to use it as a tool that can help humans to accomplish their task. Now, AI is broadly classified as machines that are used to mimic human intelligence. Now, we all know AI has subfield. The subfield of AI is called as machine learning. So, machine learning is a subfield of AI which basically learns from data without explicit programming. So, here in machine learning, we know that we have a process called as feature extraction where the important features from the data are extracted. The model learns these features and performs classification or predictive modeling task. Now a subfield of machine learning is called as deep learning or deep neural networks. Now these neural networks or basically artificial neural networks are inspired by human brain. Okay, so we all know these basic things. So deep learning is used in complex imaging and the speech recognition task. So now this machine learning can be broadly classified into three types. First thing is called supervised learning, and then we have unsupervised learning, and then we have got a reinforcement learning. So we'll look into just what exactly is supervised learning. So in supervised learning, we have data and we also have the labels associated with the data. So what do I mean by that? So here you can see, okay, you have population density. So you have data. So you have some numbers. Now along with these numbers, you have, the mortality rate, which is basically in terms of 0 and 1. So this is the label associated with the data. So a simple example would be if you have say a threshold value. So if I keep a threshold value of say 350. So values below 350 are considered as low and above 350 are considered as 1. Okay. So here you can see in this population density for 207.566, the label is 0. So you have the data, which in this case is basically numbers, and you have the label associated with it. So population density is basically people per unit area of a country. Now this data is given to this model, which we call it as a machine learning model, and this machine learning model does some prediction. Now the next question arises is how do we know that the machine learning model is giving the right prediction? So to compare the prediction of the machine learning model, we need to know the ground truth label. So here we have y hat, which is basically the predicted label, and then we have the y, which is the actual label. That's the ground truth label. So based on y hat and y, we calculate the error. So in ideal case, we want the error to be 0, but in from practical real world situation, we don't get it as 0. So now we know that machine learning models are basically divided into two parts. Okay, so in supervised learning also, or every machine learning model, I would say, could be broadly classified into two parts, that is called as training phase and testing phase. So first, you're giving these data points to the machine learning model to train it. So once the model is trained, the end goal is it should give us the right prediction. So here the goal is to predict. You have a new data point here. Okay. So in this case, it is 237.566. This is a new data point. When it is given to a machine learning model that is trained, it should give us the right label. So in this case, the label is 0. So this is called as supervised learning. Okay, the first type of machine learning model. Next type of machine learning model is basically called as unsupervised learning. So the main difference here is in unsupervised learning, you have the data, but you don't have the labels associated with it. For example, here we have population density, another column called as extreme poverty and median age. So extreme poverty is a severe lack of basic necessities, and median age is basically the middle age of the population distribution. So now you have here data, but as we saw in the previous case, we had label associated with the data. Here we do not have the labels. So we give this data to the machine learning model, and the model is now supposed to learn patterns from this data. So the most basic approach in unsupervised learning is forming clusters. So similar data points are grouped together and clusters are formed. Okay, again, you have different types of clustering, but in the basic form, it is clustering. So again, as I told previously, every machine learning model has two parts. So first is the training. So now the model learns patterns from this. And next, when a new data point is given to the machine learning model, it should able to group it. So it should either say it belongs to cluster 1, cluster 2, or 3, or so on. In this case, we can also call it as group 1 or group 2. So this is the second type of machine learning. Next, the third interesting part of machine learning which are used these days is called as reinforcement learning. So this type of machine learning is used in self-driving cars. So here we have an agent. You can see here an agent. So this agent, it interacts with the environment. So the interaction of the agent with the environment can be called as actions. So here the agent is not explicitly trained to take a specific path. Instead, the agent takes random paths. Now, every time when the agent takes path, so it gets a reward. Now, the reward could be positive, or in the most basic sense, we can have a reward to be either positive or negative. So the positive reward would be if the agent is moving in the right direction. Okay. For example, if you consider here, you have an agent, and if the end goal of the agent is to reach here. Okay. So we could give in this case, the reward when it reaches to this point has +1, and when it reaches to this fire is basically -1. So now here the agent interacts with the environment and learns from trial and error. So here we can see, okay, for as a human, we can clearly understand, okay, this would be maybe the one path that agent could take. But as I told you that the agent is not explicitly trained. So it takes random paths. For example, it took say 2 steps in this direction. Ideally we would want the agent to move this way, but agent it is possible that agent can move back as well. So now here it tries to explore. So there is a concept of exploration and exploitation in reinforcement learning. So ultimately we have an objective function and we want to maximize the reward, and the agent eventually reaches to the goal. So this type of machine learning is, as I told you, is used in medical imaging as well, and it was also used to beat the best chess player. Now, okay, focusing now that we know the basic types of machine learning, now we want to apply, these concepts for health disparity. Now, what exactly is health disparity? So we can see that health disparity is a difference in health outcomes. For example, today I'll be discussing a simple data set on COVID-19. Now, COVID-19, is a pandemic, all of us know. Now, this COVID-19 has affected different population group in a different way. Okay, it could be, for example, say example like US. So here we have maybe people who belong to say white, and say maybe people who belong to black community. Now, the same COVID-19, okay, the health outcome or the effect of health could be different for say people belonging to one group compared to people belonging to another group. So there is a difference. So difference in health outcomes and also the access to healthcare. For example, a set of people who are financially, more stable, so they could have better healthcare compared to people who do not, are not very stable in their finances. So here we are focusing on the difference in health outcome and access to healthcare across different populations. So we have different populations, and how are these populations influenced? So these populations are mainly influenced by the social, economic, and environmental factors. So this is a real problem. The health disparity is something that is real, and we have faced this. We have, most of us have seen this, especially during COVID-19. So how could we use AI to find these patterns? So basically, AI, as I told in the beginning, is a tool. So we could use AI to extract important patterns so that we can draw some insights, and these insights could help us for predictive, analytics, to build a predictive analytics model. So let us take a very basic, data set and try to understand this. So all of us know we have a good place to get a data set, and one good, repository is called Kaggle. So Kaggle is a website where you get data sets which we can use for research purposes. So one data set that is taken here, it is called as COVID-19 socio-economic and health disparities dataset. Okay, so this is a huge data set. It has over 3 million data points. So a huge data set with 3 million data points and 100 plus indicators. And these indicators are spanning for 218 countries. So you have a very huge data set which is freely available, and it's a real world data. So now, as I told you, it is basically from COVID-19. So this data set, it compiles the indicators to analyze. So the end goal of this data set is to analyze the impact of socio-economic and health factors on COVID-19 outcomes, okay, across different countries. So that is the primary goal. So now what we want to do is we want to build a basic machine learning or AI model. So what are the different steps in a to build a complete end-to-end machine learning model? So the first step in building any machine learning model would be in is data cleaning. For example, when we take these data sets and when we use it in an academic environment, okay, for example, in our classroom, so this data set will be very cleaned, but in a real world situation, once you collect the data should be pre-processed, so data will not be in a form that you can apply the machine learning model to the raw data. So once you have collected the data has to be pre-processed, and then it goes through a process called as feature engineering. For example, in the previous slide we have seen, we had say 100 plus indicators. So practically, it may not be possible to build a machine learning model with 3 million data points and 100 plus indicators. So now we need to perform some feature engineering to select, which indicators are important for our analysis. So how do we do it? We do it by performing EDA, that is exploratory data analysis. So once we have, collected the data, we have pre-processed it, we have done the feature engineering, and then we have done the exploratory data analysis. The next step would be to build the machine learning model, okay, the actual model that we want to build. So we have built the machine learning model, and then we want to validate it. So we want to know how good our machine learning model is. So as I told previously, to understand the accuracy of the machine learning model, we usually use something called as a confusion matrix. In confusion matrix, we have true positive, true negative, false positive, and false negative. So we perform validation, and once we have performed validation, we get the end results. So these end results can be deployed. Now, to deploy a machine learning model, we could use any cloud service provider. For example, AWS or GCP or Azure, any of the cloud service providers could be used to deploy the machine learning model. So this is the complete end-to-end pipeline. So now looking into deep learning. So machine learning has been there for many years, but these few years we have been using a new type of machine learning, or I would say a subset of machine learning, and that is called as deep learning. Now, as I told you, deep learning is basically inspired by human brain. Okay, so the main difference between deep learning and machine learning is here. Okay, in deep learning, the feature extraction is automatically performed by the artificial neural network. Okay, so the artificial neural network, which is inspired by human brain, automatically extracts the features. Now, for this deep learning network to give good results, there are two important things. First thing is you need large amounts of data. Okay, so if we look into the basics of artificial neural networks, these models, the fundamental models are not new. They were available since 1980s. But these days, maybe in the last decade, the artificial neural network is widely used because of the large amounts of data that is available today compared to the data that was available, say, 10 years ago. So that is one important factor. Second important factor is the growth in computing, the computing capabilities that are there. Okay, for example, we usually use GPUs, or these days we use TPUs, tensor processing units, right? So these advancements that are available were not available, say, about 10 years ago. So that is why these technological advancements in computing and the large amount of data that has been available, we are able to apply the deep learning models. Okay, so we'll try to take an example and understand this in greater detail. Okay, so here, as I told you, in deep learning model, it is inspired by human brain. So we just call it as artificial neural network. And one particular basic model that we use is called as CNN. CNN stands for convolution neural network. So we'll look into these basic concepts in detail today. Okay. So going back to the data set, as I told you, we are using the data set from Kaggle. So what is the aim? The aim of this data set is to predict. So we want to do a predictive modeling. So here the model wants to predict the total deaths per million. That would be the target variable and the key indicator of COVID-19 impact. Now for our analysis for this prototype, just to understand the concept in greater detail, I have taken, say, 6 key indicators. So first one is called as GDP per capita. So that basically it reflects a region's economic strength. So we have been hearing about GDP, right, these days. So that basically indicates the economic strength and healthcare investment, because we are talking about health disparity. So for example, COVID-19 was a pandemic. It affected almost every country in the world, but the effect that was there is different in different countries. Okay, so one of the major region is GDP. Next important reason was population density. So some of the countries are densely populated compared to other countries. Okay, so population density. Next, extreme poverty, again, that's another region. Next is the place we have seen the median age of is 50, and we have portion of population age 65 or older, because we have seen that COVID-19, during the pandemic, the senior citizens were affected more badly. Okay, and the next is portion of population age 70 and older. So these are the 6 important parameters that we have taken. So first we have collected the data. Next, the data goes to the pre-processing stage. Okay, so here we extract features and target. Okay, so usually features are given by x. So x is equal to okay features data. So what do we mean by that? We select the important columns, feature columns that are there from the data set. So that is basically the features, and y is basically the data. So you extract the target variable. So here you can see a screenshot of the 6 columns that we have selected: GDP per capita, population density, extreme poverty, median age, aged 65 and older, and 70 and older. Now, as I told you, in the real world situation, the data will not be cleaned. Ideally, what we want is data that is there like this in the first row. But here you can see in this row, the second row here we have not a number, NaN. So that is why we cannot give this data in a raw form to the machine learning model. So what we need to do, we need to perform data cleaning. So now that we know this is our X, which is basically our data, and this is basically our Y, which is the target variable, we have defined these things. Now we want to perform data cleaning. So one of the basic approaches is, okay, fill the missing values with mean. Okay, so this is like a very basic approach. So we can use mean or k-mean imputation, different techniques, so we can use mean for each feature slash target variable. So we can do that. Another process would be is to standardization. Now, why do we need to do standardization? If you don't do standardization, then what would happen is some columns will have more effect compared to other columns. So for example, if you go back here, you can see here, we have here 6 important columns. Now among this GDP per capita, you have here 2,442, a larger value, whereas extreme poverty here, the values are say 15 and 12. Now if you compare this column with this GDP per capita column, if you use it in a raw form, then every time this particular column will have more effect compared to these columns because the values are lower. So that is why what we need to do is we need to apply standardization. Okay, so a standard normal distribution where we consider mean to be 0 and standard deviation as 1. Now that we have cleaned the data, we have done standardization, the next step would be is to split the data. So in usual machine learning models, we split the data into 80-20 split. So 80% of the data would be used for training, and usually 20% of the data will be used for testing. Now, in any machine learning model, the end goal is to give good results on the test data. Giving good results on the trained data does not really help us. Okay, so getting good results on the training data, and if the model is performing very poorly on the test data, then it is called as overfitting. That is, the data is trying to not trying to learn, basically trying to memorize. A simple example would be, okay, we give say we take a class, no, we give some important questions for students for the exam. Now say a professor or a faculty member has given say 10 questions. Now if the student does not understand the logic behind these 10 questions, then if the same 10 questions are asked with same number, the student is able to memorize it and give the right result. But what we want is, we don't want the student to memorize. Instead, we want the student to learn. So here also the same example, we don't want the machine learning model to memorize. Instead, we want the machine learning model to learn, okay, patterns from the data. So again, there are different approaches. So we can again divide that 80% of training data also into say 70 and 10, where 10% could be used for validation to avoid overfitting. Then again, there are many other techniques we can use. We can use dropout, where some of the connections of the neural networks are dropped. Again, all these techniques are used to avoid overfitting, because the ultimate goal is the model should give good results on the test data. So in our case, we had 64,675 total data points, which we have divided into two: 80% of training and 20% of testing. Okay. So next, okay. So now what we are trying to understand is what are the different layers in this artificial neural network. So, in a very basic sense, the artificial neural network has first the input layer, and then we can consider we have the output layer. So you will have input, you will have output. Now between input and output, you will have multiple hidden layers. So here you have hidden layers. So everything in artificial neural network is to design how many hidden layers are required, how many nodes are required. Now these circles that you see are called as nodes, So how many nodes are required? So that is called as a architecture. That is called as designing a neural network. Okay. So we'll look into the basics of it. Okay. So you'll have these connections from the input layer to the hidden layer, and in a very basic sense it is from hidden layer to output layer. So from this diagram we understand that the most important part is this circle, which is basically the node. Okay, so in real world situation we can have one say hidden input layer, multiple hidden layers, multiple hidden layers, and then you can have the output layer. Again, output node, if it is just for binary classification, just one node would be sufficient. But we know that in real world situation, most of the cases it will not be binary. Instead, the data will be categorical. So we could have multiple nodes in the output layer. We'll just try to understand what exactly is this node and what exactly happens in this node. Okay, in a very basic sense, the most important or the fundamental building block of artificial neural network is node, and that is we call it as neuron. Okay, so this is basically the node. Now, what happens in this particular neuron? This neuron basically gets some inputs. So these inputs, we can call it as input 1, input 2, up to input m or n, okay, whatever. So you have, in this case, we have got m number of inputs. So in a very basic sense, this m number of inputs are given to this neuron or node, and we get one output. Now we want to understand what exactly happens inside this particular circle. So in a very basic sense, you have input here, input 1 to input m. Now these lines are connected. These connections that you see are called as synapse. You have weights associated with them on this line that we write. For example, here for w1, if we write here, say for x1, we write weight w1. So that will act like a scaling factor. So it will be x1 w1 plus x2 w2 plus xm wm, which will be given to this node, which we'll understand in the coming slides. So coming back to our example, so here we had 6 important columns that we have considered: GDP, population density, extreme poverty, and so on. So that is basically the data. And then we had the target variable. In this case is population, or sorry, a total deaths per million. Okay, and y hat, as I told you, is basically the predicted value, and y would be the original label. Okay, so now we'll try to use these values to the artificial neural network. So in this case, as I told you, we have 6 inputs. So we have here x1 to x6, and y is basically our output, which is basically total death per million. So if you go back to the neuron, so we have here 6 arrows that will be coming to this neuron, and you will get one output, that is total deaths per million. But we want to understand what exactly is happening inside this particular block. Okay, it is if you just see in a very basic sense, it's not just all inputs are coming and you are getting one output. There is some operation that is happening inside this block. So that is what we want to understand. Now the main important thing to understand what is happening inside the block is these connections, these lines that you see. So those are the important parts. So you have, as I told you here, you have weights associated with these lines. So here you have weight can be considered in a very basic sense as a scaling factor. So whatever is, say, GDP per capita. So for example, say if GDP per capita was 100, and here the weight was, say, 0.5. So then this 100 will be multiplied by 0.5. So the actual value that goes to the neuron is 50% reduced. So now it is 50. So these weights can be considered like a scaling factor. So we need to know, how do we start? when we start, what weights we need to use. Okay, so these weights are given to this neuron. What next happens inside this particular block? If you go back to this particular block, the first thing that happens inside this block is, we can consider it like 3 steps. Step number 1 is summation, that is xiwi. So here we can see I is equal to 1 to 6 because there are 6 inputs. Weights would be w1 to w6. So a summation is taken. So it will be x1 w1 plus x2 w2 so on up till x, okay, 6 w6. So summation is taken. That is step number 1. Okay, but just by taking summation, you cannot get the output. What is the next step? The next important step is this particular symbol that you see here. That is called as phi. And we, in from mathematical terms, we call it as an activation function. Okay, so we'll try to understand how exactly this works. So first you have summation that is done. Next step, we want to know what is an activation function. And what is the third step? Third step would be the output that you see here. Okay, so we'll try to understand what exactly is an activation function. That activation function is, we can consider it like a trigger, that is like the trigger pulse that is required. So I'll show you some very basic activation functions. As I told you, this particular symbol, what are the basic activation functions that are available. Okay, this particular symbol. Okay, phi activation function. Okay, so if you see here, the very basic most activation function would be a thresholding function. Again, in real world situation, we'll be not using this activation function, but just to understand from the basic. So the basic would be, you have calculated this summation wi xi, you have calculated the summation, and for after you calculate, if you get a value as 0. Now how is it possible to get value 0 after doing summation? Because the weights can be negative as well. Okay, so if you have a negative weight, then when you do summation, for whatever reason, say if you get 0, then the most basic activation function, if you use thresholding, the output would be 1. When it is greater than or equal to 0, whenever it is less than 0, we are considering it as 0. This could be like the most basic activation function. But in real world, we don't use thresholding. Instead, one basic activation function that we use is called as a sigmoid activation function. Okay, and this is the formula. Phi of x is equal to 1 divided by 1 plus e to the power of minus x. So what exactly this activation function does? It's very interesting. This particular activation function, it ranges from 0 to 1. And for high values, so whenever this wi xi values are very high, the activation function is just giving you output close to 1. So you can see here, it is like capping at 1. And here for very low values, it is capping to 0. So that is the, it's like a squashing function that is used. So this is the second activation function. However, in most of the real world neural networks, we use something called as a ReLU. ReLU stands for rectified linear unit. So this activation function is interesting. So it takes max of x and 0. For example, here, if the value is less than 0, whenever it is less than 0, then the answer would be 0. It is maximum of either x or 0. So that means if the value is negative, you'll get the answer as 0. If the value is positive, then it keeps as it is. Okay, so that is how this particular activation function works. And that is called as a rectified linear unit. Okay, so coming back to our analysis. So in this case, we had x1 to x6, which is given to this neuron. This is the activation function. And then you have the output. Okay, to summarize, you have here x1 to x6. Okay, I've just summarized here w1 to w6. Given to this neuron, you have the activation function and you get the output. Okay, initial output would be y. As I told you, y hat would be the predicted one. Now we want to calculate the error. How do we calculate the error? To calculate the error, it's a difference between y and y hat. So as I told you, y is the actual value, which is the ground truth label. So you do a very basic sense would be a subtraction between y and y hat. So that will help you to calculate the error. Now, the most important part in this neural network is you do not get the results, or I would say very rarely you get the result in one iteration. This one iteration that you see, this is called as forward propagation. Okay, and in one iteration we rarely get results, so we need to go over this cycle over and over again, and that is called as epochs. Okay, so epoch is basically that cycle. So what exactly happens? So this is the first cycle I told you, so forward propagation. So you have here x1 to x6, you have these values, you have w1 to w6, you did the summation, you applied the activation function, you got the prediction. You got the prediction, you know the actual value, you calculated the error. Okay, so you got the output and you calculated the error. Okay, so you had y hat, which is this value. Next, you know y, which is the actual value. Okay, and between these two, you calculate the error. So E is equal to half y hat minus y whole square. Now, why do we square it? In a very basic sense? Okay, in some situations, we could have the error to be negative. In some situations we could have the error to be positive. So if you don't use the square value, what could happen is one negative value and one positive value could cancel each other, and the total error could be zero, but actually the total error is not zero. So that is why we square it. So we have y hat minus y whole square, and zero point 0.5 is basically the scaling factor. So now we calculate this error. Okay. Now after we calculate the error, so what we want in ideal case, we want is error to be zero, but we do not get error zero in the first iteration. Okay. So in the next iteration, we need to have a mechanism to change these weights, because see, if you see in a very basic sense, weight is the only thing that you can change. You can't change the input. Okay. You can change the activation function if you want, but the most important thing is the weight. So based on these error values, we perform something called as back propagation. Okay, so this error is basically back propagated, and these weights are updated. Okay, I'm not going too much into the math behind it, the partial derivatives are taken and all those things, but in a very basic sense, you understand that these weights play a most important role. So these weights are updated with the process of back propagation. The weights are updated, and again the next cycle starts. Again forward pass is done. Again a prediction is done. Again error is calculated. Again the weights are updated. So every cycle, if you see, the weights get updated. So you have y, the actual value, y had the predicted value, and in the back propagation, the weights are updated. Now, these are the actual results that we obtained, for the neural network that I discussed. So, the loss or, the error in every cycle or epoch, the loss should keep decreasing. So in this case, it's a very simple example. You have here 50 epochs approximately. You can see initially the loss value is very high, and then the loss value keeps decreasing. Okay. Yeah. Now coming back to next important concept of the research is how do we apply this deep learning for classification and in the context of health disparity. So again, we looked into one particular data set. So as I told you, the effect of these machine learning models on black population is different from say a white or of people of different origin. So we have taken a population of black people, and we are using the Kaggle data set, and we want to perform something called as liveness detection. Okay, so here we have two things. We have images and we have videos. So we have images and videos of people. In this case, it's basically black individuals, and we have the anti-spoofing mechanism that we want to use, and we want to use basically deep learning for it. Okay, so I'll tell you how exactly it works. So here you can see we have a basic, a few images. So those are selfies, those are actual images which are taken. These are videos that you see here. So they are videos. So you have videos and you have got these selfies. Now, these images are pre-processed again, and then it's given to this neural network model, in this case, basically the deep learning model, and where, as I told you, it performs the feature extraction and classification together. And in this case, the basic output sense is either it should say it is live or it is spoof. Okay, so live would be the video, right? And spoof would be this particular images. The simplest example would be you will have this iPhone or any phone, basically Android phone, any phone. We want it to unlock only when it is a real human being, right? We do not want someone to take our image and to try to unlock the phone. So first process would be here, would be pre-processing, that is extracting frames from videos, and next thing would be resizing it, so getting into the right dimension, and then applying the basic CNN model, convolution neural network model. Okay, and then we get the output. So now we want to understand what exactly is this CNN model, what exactly happens inside this particular block. Okay, we'll try to understand that in greater detail. So in a high level overview, you have these images and you have these frames of, in this case, black people, which are given to this CNN model, and we want to get the output. Okay, so now it's very interesting how the neural network model looks at images. As a human being, when we see these images, if you see these are images belonging to X can be written in different ways. So we can clearly identify that, these are different ways in which X is written. But all the image operations are basically matrix multiplication. So the smallest part in the image we know is called as pixel. So when we say 8 megapixel, right, so we have, or 48 megapixel, these cameras. Why does a image of 48 megapixel have greater clarity? Because it has more pixels. So basically 48, when we say, it is 48 into 10 to the power of 6 if it is mega. Now, every point, every pixel is basically converted into a matrix. So you need to understand, for one image, we will have a matrix of values 48 into 10 to the power of 6. That would be the raw dimension of this particular, image converted into a matrix. So from the computer point of view, if it just tries to match these two, images directly, it will say that these are not same. Okay, one-to-one matching. So that is why you just cannot convert it into, binary and do matching. Instead, what we want to do is we want to tell the CNN model that these images are belonging to the same group. CNN, in this case, is belonging to group X, and we want to get the output as X. So how do we do it? So instead of taking the entire image, what do? We break down these images. You can see here, instead of taking the entire image, we break down these images into smaller parts. Okay, and then we do the comparison. So coming back to this example here, what are the important steps in the CNN model? Now, the important steps in CNN model include something called as convolution operation, and then you have pooling operation and flattening and fully connected region. So we'll try to understand these things in greater detail. Okay, the first step would be the convolution operation. So what exactly is convolution operation? Let us consider an image and let us consider a small matrix for it. So in this case, it is 3 cross 3. 3 cross 3 indicates you have 3 rows and 3 columns. Now, this particular matrix, it goes through a feature extractor or a kernel. So in this case, we have a 2 cross 2 kernel of values, say 0, 1, 2, 3, and a convolution operation is done between this X and H. Okay, and what exactly is this convolution operation? So here you can see this 0 is multiplied with this 0 plus next this 1 is multiplied this 1 plus, so pixel by pixel multiplication is done, and you'll get the final value. So this is the first step, convolution operation is done. Similarly, next, it's taken, values are multiplied, and you get the results. So this is the first step. Step number 1, convolution operation is done. So we use a feature detector or feature extractor is applied on this image, and then you get the, output after convolution, which we also call it as feature map. Okay, so this is step number 1. But as you see here, after you have got the feature map, we need to next try to reduce the dimensionality, because if you consider just by convolution operation, if you want to, process it, it will be very difficult. So if you want to reduce the dimensionality, we need to apply some technique, and that would be our step number two. The step number two would be applying a technique called as pooling operation. So this is the summary of step number one. You have input image, you use, convolution layer, you get multiple feature maps. These are created in step number one. Now in step number two, what we want to do is we want to consider this output and we want to reduce its dimensionality by applying next operation, and that will be called as pooling operation. Now what we could also do is this particular feature map, we could apply an activation function. Okay, another way to reduce would be if you want to get rid of all the negative values. Sometime back I told you how the rectified linear unit activation function works. Rectified linear unit, all the negative values it will make it as 0, and positive values will keep it as it is. Okay, so that is the activation function which we studied some time back. So if you look here, you have the feature map here. So first thing is you have here 0, so that value will remain as it is, 1 will remain as it is. Okay, all the values which are 0 or positive will remain as it is. But if the values that are negative, for example here you can see we have -1. Okay, so -1 will become 0. So we have now eliminated all the values which are negative. So that will be called as a rectified feature map. That is feature map, you are applied the rectified linear unit with the activation function. Okay, now that we have done this process, so we use the image, we did the convolution operation, we got the feature map, we applied the activation function, we got, in this case, rectified linear unit has the activation function. So we got the rectified feature maps. And after that, we apply the pooling operation. Okay, so how does the pooling operation work? Here we have the rectified feature map. Now what we want to do is we want to just, because it is max pooling, again, there are different types of pooling operation. Here we are focused on one type, which is called as max pooling. In max pooling, what happens is among the 4 values, the maximum value will be selected. So in this case, it is 0, 1, 0, 1. The maximum value is basically 1. In this case also it's 1. Okay. Now here you can see the maximum value of this is basically 4. So the idea is, see, whenever we do dimensionality reduction, previously, in traditional machine learning approaches, we used to use PCA, principal component analysis. So whenever dimensionality reduction is done, there will be some loss of data. But here what we want to do is a trade-off. The idea is the maximum value will have more significant features compared to the values which are, less than the maximum. So that's why we want to consider only the maximum value. Again, this is not the only method, but this is one of the method. And this is basically the step number 2. So just to summarize, you had input image, it goes through the convolution operation. You got the, the feature map, and then we applied the rectified linear unit, we got the rectified feature map, and then we applied pooling operation, and then we get the output of pooling. And the next last 2 steps include flattening. So here, this is the output of pooling operation. We convert it into a column vector. So this is called as a column vector, and we flatten it. So that is the step number 3. So once we have completed the flattening process, so just to summarize the steps was input, convolution, pooling operation, and next we got the, flattening operation. We got the column vector. And the next last step is it's called as a fully connected region. Okay, so what do we mean by fully connected? A fully connected is when, say for example, here you can see the first node of the hidden layer, where every node of one layer is connected to every other node in the next layer. That is called as a fully connected convolution neural network. Now again, there are advantages and disadvantages as well. If it is fully connected, if you keep it as it is, it will be able to extract more and more features. But again, the idea is of the neural network is not just to extract more features on the training data, but it has to learn patterns from the training data, because we don't want it to memorize. Instead, we want it to learn. So that is why to drop, so there's a concept called as dropout. So when we use a dropout has 10%, that means 10% of these connections are randomly dropped. The idea is again so that it's able to learn the patterns but not just memorize it. So this is basically the step number 4. So 4 important steps which are there. Okay, so in the CNN model. Okay, so coming back to our example, we had two set of data points. One was selfie, okay, which in this case is basically spoof. Selfie is basically a person using an image to try to unlock a phone. Okay, so that is basically a spoof, whereas if it was a video, it would be basically live. Now what exactly happens in this particular layer and how exactly the final decision is done, I would like to explain this in greater detail. So if you see here, you have some hypothetical values. You have some values here. These are some random values that are there in the not the output layer, the last hidden layer. So now how does it decide that if this for this particular input, this should be the output? How does it decide? So what it does is if you just take this output in a raw form, it will be something like this. It will be say 1.23 and 0.23. So it is difficult to set a threshold value if it is in a raw form. So what do we do here is in the output here, we apply an activation function, and that activation function is called a softmax activation function. So what is the advantage of softmax? It generates output in terms of probabilities. So here we know that if it is two classes, the when we add the probability, it will be 1. So now because we get the value in terms of probabilities, for example here it is 0.73 percent the probability that it is a spoof, and 27% probability that it is live. In real world situation, what we would like is we would like that it should be 100% sure, but neural network is not giving us result in terms, it's not a deterministic approach. It is a, giving output in terms of probabilities. So even though input image, we know in this case it's a selfie, it should be a spoof, we are expecting it to get say 95% or 100% sure, but it doesn't work that way. It still, you have some possibility that it is live. So in this case, if you consider this example, it is 73% sure that it is spoof and 27% sure that it is live. Okay, next, given a video, we know that it is live. It goes through same example. You have this hypothetical values. Again, we apply the softmax activation function. And in this case, it's important to note that, the raw values could be negative as well, because I told you sometime back that the weights could be negative. Okay, so again, we cannot use the raw values. We apply the softmax activation function. I have not put too much of math, so it'll be easy for you to understand. Basically, the softmax activation function will give you the output in terms of probabilities, and in this case, you can see, okay, the probability is more for live, so that is why it is basically giving us the answer as live. Now, once this process is done, okay, we want to calculate the loss. So how do we calculate the loss? We have seen previously in the previous example, the loss or error was calculated between difference between the actual value and the predicted value. In these cases, we use something called as cross entropy. Okay, just in case if you are interested, cross entropy basically quantifies the difference between the predicted and the actual probabilities. In case if you're interested in the math formula, so this is the formula behind it. So where p of x is basically the actual value, which could be either 1 or 0, and q of x is basically the predicted probability, that is the softmax output. X represents each class. In this case, if it is say MNEST dataset, you have digits say 0 to 9. If it is a binary classification, it will be say 2 classes, and then the negative value ensures that the loss is non-negative. Okay, and then the summation is taken. So these are the important steps that are there. Next, as I told you, you don't get the results in one cycle. What is done is gradients are calculated, and in the process of back propagation, those weights are updated and the model performance is expected to improve. Okay, the same process is done for selfie, the same process is done for video. So again, we have seen this slide previously. In the process of back propagation, what happens? The weights are updated, and ideally what we want is in every cycle to improve. But in real world situation, every cycle it may not actually improve. It is possible that it keeps improving, then it goes down, again it goes up, again it goes down, and so on. So here a key consideration is how many epochs, how many cycles you want the data to go over. So again, we can select the number of cycles. Also, we have a concept of early stopping. For example, if the model is not learning for say 10 epochs or 15 epochs, then running it for 5,000 epochs is a waste, right? If the network is not learning. So we have a concept of early stopping, which we could use, to avoid unnecessary use of, computation. So these are the important things I would like to, share. I think I'm almost done with my time, and if you have any questions, you are free to ask me. Yeah. Thank you.
Hello.
Yes.
Participants, any questions? You can ask through chat also.
Yeah, you can ask to chat, or if you want to reach out to me later, you can, reach out to me through email or LinkedIn or any of the, networks. I thank, Ravichandran sir, Dr. Ravichandran sir, for giving me this opportunity to share some insights. And so I also, work on some advanced research, which is on attribution-based confidence metric and other things. Which is applied for histopathological images, okay, breast cancer images and things like that. Yeah, so these are, there are many things I could explain. So some of the research when I was a postdoc researcher, that was funded by NIH, and things are, some of them were from the US Army Research Lab and Stanford Research Institute and so on. Today I just covered the basics of these networks, because I thought it will like good to get a good overview of things. Yeah. Thank you, everyone.
Thank you, sir, Steven Fernandez Garu, for giving wonderful session. Enlighten our participants with your knowledge, with your insights on artificial intelligence and its applications in real time. Thank you very much, sir.
Thank you. Thank you.
Thank you. Have a good day.
Bye.
Thank you, sir. Nice. If possible, please share the PPT, sir. I think already.
Okay. Yes.